What's this, Brady?
It's like a graph or like a joined up circles.
No, this is an ant. You can see the antenna up there, and then this is the body of the ant.
Oh yeah, okay.
We're going to place odd consecutive integers starting with 1 into this ant. So what are those odd consecutive integers starting with 1? Well, we need 1, 3, 5, 7, and 9. We're going to be placing them in here. So what number do you want here?
7.
7. In here?
3.
In here?
1. Let's put 9.
And?
5.
Okay, so this is an example of a failure. We're going to look at 5 minus 1. That is 4. 9 minus 1. That's 8. 3 minus 1. That's 2. Everything looks different so far, looking good. Sadly, 7 minus 3 is also 4. So we failed. This is an example of a failure. Your job is to try to make all of those differences different. If I go 7, 3, 1, 9, 5, then we have 4 and 8 and 6 and 4. Oh, wait, no, this is still a disaster. I wonder if this is even possible to solve this ant. You're okay to fail, but I'm supposed to be succeeding here. Okay, let's go 9, 1. Now, maybe I'm going to put the 7 up here, and the 5 here, and the 3 here. Does this work? Yeah. This looks good. So this is 9 minus 1, that's 8. 7 minus 1, 6, 4, and 2. We're all different. We are successful. We get to ride the ant. So this is part of an unsolved problem from 1967 called the graceful tree conjecture. But it belongs in every elementary school's curriculum whenever they're learning subtraction. So the general problem is, given any number of connected circles, so they have to be connected, any number that you want. They have to be connected, and there can be no loops. So this would be a fine insectoid to solve. Let me show you a loop. So you could ask, can this be solved? So this might be solvable, it might not. But it's certainly not the graceful tree conjecture. The graceful tree conjecture means that there's no loops.
Okay.
But why don't we try to solve this? So now we need 1, 3, 5, 7, and 9 into here. Can this be solved? Consider how many even numbers you can get. What's the biggest even number that you can get as a difference between these?
8.
8, yeah. 9 and 1, the biggest you can get is 8. What's the second biggest number that you can get?
6.
Yes. And the third biggest number? 4. And then the last one is 2. There are only 4 different numbers that you can have. But how many lines do we have to satisfy? We have got 5 lines. We've only got 4 even numbers to distribute between these 5 lines. So no matter how you distribute these odd numbers, you are always going to end up with a duplicate. So here we have 8, 6, 4, 2, and 4. Again, we've ended up with a duplicate over here. So this starfish cannot be solved. It will fail every time if we have n circles and n lines connecting them. We will never be able to solve that. We can potentially solve for n circles, in this case 5 circles, and n minus 1, maximum of 4 lines. We sometimes can solve for that. So 5 circles where you could solve it. So here's a butterfly. Here are 5 lines and 1 less connector. So this could be solved. What about this? 5 circles and 4 connectors. I don't know if this can be solved, but this might be able to be solved. The graceful tree conjecture doesn't include loops, but this is still an interesting question. I don't know the solution to this. So the graceful tree conjecture is one where you have all of your circles connected, so you don't have an outlier here, and there's no loops. So that is guaranteed. If you've got n circles, you're going to have n minus 1 connectors. So here we've got 1, 2, 3, 4, 5, 6, 7 circles, 1, 2, 3, 4, 5, 6 lines. And this is what is unsolved. Whether for n circles and n minus 1 lines where there are no loops, can you always put in there odd consecutive integers such that the difference between all connected circles, all of those differences, are different?
What's it not proven for? Like, surely you mean for all designs of tree, or?
Yeah, for all insectoids or all trees that you would care to design. So this one for 7 has been solved. This is an example of 7 circles and 6 connecting lines. There are actually 11 different ways that you can do that. So here we have the 11 different ways to have 7 circles, all connected, no loops. What is unsolved is going for more circles. If you go into 30 or 40 circles, are these all solvable? This has been an open conjecture since 1967.
So presumably, Gord, if I start having more circles, like 30 circles or 40 circles, the number of insectoids possible must just get massive.
Oh, it explodes. Exactly right.
Up to what number of circles is it solved for?
There are individual cases that have been solved. For example, I can put a circle in the middle and I can add any number of circles on the outside that you want, and this is always solvable. And I can prove that quite easily. I can put a 1 in the middle, then I can go 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23. And you can imagine I can keep on going here. And this is always solvable because these differences are always different. I could also put the largest number in the middle. 23 could go in the middle, and then I could distribute the other numbers all around. Always solvable. Another example of a species that is always solvable are snakes. So you could imagine a snake of any length that you want. And these are always solvable. You might want to try this. You can start with 1, and then you can go to your largest one. I'm actually going to just skip. I'm going to go 1, 3, 5, 7, and then I'm going to come back. 9, 11, 13. Here we have a difference of 12, a difference of 10, a difference of 8, a difference of 6, a difference of 4, and a difference of 2. All snakes can be solvable just by replicating that pattern. There's lots of species out there. Not everything is a snake. Not everything is a sea star. There's lots of species out there. You could very easily create and explore new species. For example, what happens if we have something crazy that, 2 sea stars joined with a long dendritic chain? So is that solvable? You can imagine that these can get very, very complex very, very quickly. And most species, by the time you get to 40 circles, most of those insectoids, very difficult to solve.
So presumably, Gord, if this is still an unanswered question, that means there's yet to be a species of tree found that is definitely unsolvable, because that would ruin it.
That's correct. We have not found an example that doesn't work, but that doesn't mean that it doesn't exist. There are plenty of mathematicians who believe that that tree exists, that there is a tree out there that cannot be solved.
Would you be happy or sad if one was found?
Oh, I would be thrilled if one was found, because I do this with my elementary school kids, and after a week of them struggling to find one that can't be solved, I would love to say, and here we have